Hello everybody, my name is Garrett and my lab partner was Carly. For today, we're going to be going over the part 1 of the spectrophotometry lab, which we did in class as the introduction for the other two parts. Now, spectrophotometry is the method of measuring how much a chemical substance absorbs light by measuring the intensity of the light beam as it passes through the sample solution. So as the light passes through, whatever light ends up getting through is then registered by the machine and converts that into a number that we can use to determine how much light has been absorbed versus transmitted. Before we continue, it's really cool to learn about the history behind this. In 1940, a guy named Arnold Orville Beckman, not to be concerned or mixed up with George Orwell with 1984, which is a really good book. I highly recommend. Back on track. Arnold Orville Beckman and his colleagues invented the spectrophotometer, and it turned out to be one of his greatest things ever. It was great. It was used in a lot of places. Clinics, industrial laboratories, chemistry, biochemistry labs. It was great. And today, the modern spectrophotometer is actually used for more things than just science purposes. So, medicine, determining different substances in medicine, crime scene investigations for different substances at crime scene investigations. There are many applications for this. As we continue, before 1940s, chemical analysis through the same process, which was actually much, much harder, was only about 25% accurate, and it took forever to complete. We're talking days, weeks, months, maybe not years, but it was a pretty long time. Now, Beckman's DU spectrophotometer, which was actually his final model, took minutes to complete and was 99.99% accurate, which is an incredible difference over the 25% for the chemical analysis they used to do. Now, one of his first models of the spec, or the spectrophotometer, spec is short for spectrophotometer, was the Model B. It had some problems that required a change to the design, where the quartz-side prism was being used versus a glass-sized prism. So they had to figure out which one to use to produce a better clarity. And then the Model C raised wavelength resolution in the ultraviolet range. So as you got up towards the higher nanometer, lower size nanometers, it would get a little fuzzy, so you'd have to increase accuracy for that, which was cool. And then in 1941, there was a Model DU, which was finally produced with a hydrogen lamp, which also improved accuracy even further. So this is then. Got the outer case, both have an outer case. A lot of things are similar, I'm sure. The only thing different is this is now digital, so you don't have to worry about reading any sort of analog or hard to maneuver things anymore. And this actually comes with a easy to understand user manual. Now, the purpose for part 1 of the lab was to determine the correlation between the color of a compound and how specific wavelengths of light are absorbed or transmitted. And it was important to know because different concentrations of compounds affect the amount of light absorbed into the solution or transmitted through the solution. Another reason why we're doing part 1 is just to learn how to use the Spec 20, because I've never used one before until this class, and it was a lot of fun. So starting the Spec 20, had to turn it on for about 15 minutes to get all the lights whirring and gears moving so that everything was nice and warmed up and ready to go. We went and got 6 cuvettes from a cart and cleaned them with deionized water, and then dried them with Kim wipes because it's anti-scratchy and gets all the fingerprints off, so it's a nice clear glass cuvette. We then filled each cuvette separately with clear deionized water, starting on the left, diluted pale red liquid, yellow liquid, green liquid, and blue liquid, all in a rack in that order. Then we went to the Spec 20 and we set it to a wavelength of 525 nanometers to start out, just to see how to use the Spec 20. We inserted the cuvette with the water and set the machine to 100% transmittance. And the transmittance lever, oh, wrong way, is right here. So as we would put our sample cuvettes into here, we would have to clear it with a blank first. So a water cuvette would go in. This line would line up with another line here, so that every time you put a cuvette in, it was reading the same passage through the cuvette. And then this is our readout screen. So when this was set to transmittance, it would show us the percent of light being shown through whatever was inside of this compartment. And the sample compartment is just that. It's a sample compartment. And this is the wavelength selector. So this is how you would find the wavelength. This is to adjust the zero. So as soon as you turn it on, set the numbers to 0 so everything's as accurate as possible. Now as we continued, we put the pale red solution into the Spec 20 after setting it with the clear water, and we got a reading of 66.4% transmittance. Then we took that cuvette out, we reset it to 650 nanometers, and we adjusted the filter lever. Now not all of them had a filter lever, but they were on ours over here, and you would adjust that to increase accuracy at the higher end of the spectrum for wavelengths. Lower end. 650 is bigger than 425. Anyway, we inserted the second cuvette with the pale red liquid into the 650 nanometers and got a reading of 78% transmittance. So 78% of light was being transmitted back through the cuvette. Now, the process stated above of putting the clear water in, setting the transmittance to 100, setting our lever and wavelength, all happened every time we changed wavelengths. And we started at 450 nanometers and ended at a wavelength of 650 nanometers. So starting small, getting big. This is our data table, all nice and color-coded. So we have red, yellow, green, and blue for the 4 colors that we did. We have percent transmittance in the first column of each color. We have the wavelength in the second column of each color, and the absorption in the third part of every column. Now the data from the percent transmittance was then put into a formula, which was 2 minus the log of the percent transmittance, and that's how we got the absorption. So absorption equals 2 minus the log of percent transmittance. Now our results were really cool. So on the lower end of the spectrum, I should say the higher end because smaller wavelengths have more energy. On the ultraviolet range, yellow, visible light range, that's about yellow, starting at 450 and 500, it was absorbing a lot of the other colors that were not red. So as we got to infrared and red, those lights were then transmitted. They were transmitted through, because the way light works is anything that is not being shown is absorbed, and anything that is being shown is transmitted or reflected, and that's what your eye sees. So here you can see the green vial, a little bit of the ultraviolet, but as it goes through, the colors towards blue, green, coming up towards red, and then it absorbed a lot of the infrared. Blue vial, as we go through, did not want anything to do with ultraviolet and everything to do with, nothing to do with ultraviolet and everything to do with red. So it absorbed a lot of the red and transmitted a lot of the ultraviolet. Now the yellow, which is kind of odd, ended up absorbing a lot of the beginning of the visible light spectrum, the ultraviolet and stuff like that, and just completely reflected everything else as we continued up. On the other side of that, how much was transmitted through? So at 640 nanometers, that is about the wavelength for red, all of these stuff here was being transmitted through, whereas, like we said before, the percent absorbed is all in the upper end of the energy spectrum, or ultraviolet, greens and such like that. When you get to green, gets kind of crazy. Same with yellow, gets kind of crazy. And with blue, really transmits the ultraviolet and blues and really absorbs the reds. Now from the graphs, it can be concluded that when absorbance is increasing, so when this is really high, then transmittance is really low because not all the light is going through the substance. Now in the green and blue, they're both very similar in absorbance. You can see they're almost identical because they're very similar in wavelengths. Really close on the color spectrum. And the yellows and the reds are very different, and that is because they're on far away spots on the color spectrum. So although red did absorb some of the blues and greens, yellow absorbed more of the purples and transmitted a lot of the other colors, as you can see by these two graphs. Thank you for listening to the presentation today. If you have any questions, feel free to ask in an email, because unfortunately I couldn't get into class, but I appreciate this opportunity to re-up and complete this assignment. Thank you very much. I hope you have a wonderful summer. Thank you very much.